Start. Let's start. And so, actually, will we record the lecture or we will not?
Yeah, no problem for me.
Yeah, okay, great. So then let's start. And so it's my pleasure to introduce our today's speaker, Tommaso Botta from ETH, and he will be speaking about Maulik-Okounkov Lie algebras and BPS Lie algebras. So please.
Yeah, so thank you very much to the organizer for the invitation. It's a pleasure to give a talk at the M seminar. And yeah, so today's talk is about the Maulik-Okounkov Lie algebra and the BPS Lie algebra. So hopefully I'll manage to explain why these two objects that kind of arise naturally in studying enumerative geometry problems are connected and how they are connected. So most of the talk is based on recent joint work with Ben Davison on the archive. And okay, so let's start with the motivation. So I enjoyed watching a series of lectures from Lucien Ennekart on these called lectures on cohomological algebras for two Calabi-Yau categories and applications. They were given on this seminar, at this seminar. And so I think these are a great point to start, because so I think that Lucien did a fantastic job at explaining that whenever we are given a two Calabi-Yau category C plus some mild conditions. So Lucien, in his joint work with Ben Davison and Sebastian Schlegel-Melia, so they defined a cohomological algebra, or well, more precisely, a shift-theoretic version of a coha, which lives in the derived category of constructible sheaves on MC, which for me is the good modular space. So it parameterizes semi-simple objects in my category C, my chosen two Calabi-Yau category. And so, as I said, this is a cohomological algebra. So in particular, it is an algebra object in this derived category. And here, the monoidal structure, so this is the monoidal functor entering the definition of the monoidal structure, comes from taking direct sums of semi-simple modules. And so in today's talk, we'll be interested in understanding something about this cohomological algebra when C, so our two Calabi-Yau category, is a very specific category. So in particular, we set C to be the preprojective algebra. So more precisely, I should say the category of representations of the preprojective algebra of an arbitrary quiver Q. So for me, Q is an arbitrary quiver with finitely many vertices. And so in their work, these guys prove that one can study, in particular, two perverse sheaves. So the so-called BPS Lie, so the BPS, the sheaf of, so the perverse sheaf encoding some kind of Lie algebra, and the sheaf of BPS algebra. So they can both be seen as something with the cohomological algebra as a target, but they kind of come from two different worlds. So in the case of the sheaf of BPS algebra, or maybe I should say BPS sheaf of algebras, but anyway. So this is obtained essentially by some perverse truncation of the coha. So it's some truncation of the cohomological algebra in this shift theoretic at this shift theoretic level. And this is a purely two-dimensional construction, so it is in the realm. Everything is well is done in this framework of two Calabi-Yau categories. But then there's also a smaller object, a small perverse sheaf, this BPF sheaf encoding some underlying Lie algebra. And this essentially comes from dimensional reduction, so the one that Lucien explained in his series of talks, and in the theory of critical cohomological algebras. So critical cohomological algebras for some triple quiver with a canonical potential, the same as the 2D coha for the preprojective algebra. This is essentially the idea behind dimensional reduction. And working in that setting gives rise to these BPF sheaves of Lie algebras. And so the idea is that once we are given these sheaves, we can try to take derived global sections and see what happened. So in particular, passing to derived global sections, we get these morphisms. So these are graded with respect to z times the connected components. The connected components of my good moduli space. And so the idea is that as soon as we pass to the derived global section, we really see how Lie algebras and universal enveloping algebras emerge. So in particular, what Hennekart, Davison, and Schlegel-Meyer show is that they can construct the so-called BPS Lie algebra. So this is just the derived global section of the BPS sheaves here. And also its universal enveloping algebra as derived global section of this sheaf theoretic object. So it is, their construction is very cool and abstract, at least from my perspective. But it would be interesting to understand more about this BPS Lie algebra. And today's goal is really to dig into this subject. So before ending this introduction, I should stress that this BPS Lie algebra obtained by considering derived global section of the BPS sheaf is the positive half of a GKM algebra. So more precisely, it's some kind of a Brochard Lie algebra whose positive part is this one. And it is also interesting that the Chevalier generators of this generalized Kac-Moody algebra are obtained as intersection complexes on this good moduli space. So, and the last ingredient I should recall you is that due to Davison and Mainhardt, we have some sort of PBW theorem for the cohomological algebra, saying that, again, the cohomological algebra, so this is the cohomological algebra, is isomorphic as a vector space to this symmetric algebra. So here we are tensoring the BPS Lie algebra. So this is the BPS Lie algebra. And we are tensoring with the cohomology, the C-star equivalent cohomology of the point. So this is just polynomials in one variable. So let me also make a final remark before ending this reminder of Lucien's lectures. So I think that in Lucien's lecture, everything was defined over rational numbers, essentially. So, however, it is important for us today that everything admits deformations via torus actions. So in particular, what we can do is that we can consider a torus T acting in some way on our moduli space of objects, of semisimple objects. And by means of this torus action, we can construct some kind of T-deformed cohomological algebra. So in particular, both the space is deformed and also its multiplication. And we can also consider some kind of deformed version of the Lie algebra. However, it turns out that the Lie algebra is not deformed at all, in the sense that this construction of the BPS Lie algebra is rigid enough to ensure that so if we try to take the what a priori could be some kind of theta form version by means of this torus action, we simply recover the original Lie algebra up to an extension of the base field. So this
When
is...
you say deformed, do you mean commutative deformations or non?
No, it will be non-commutative at this point.
Okay.
So, yeah, exactly. So, okay, this was a very quick and dirty reminder of Lucian lectures, but hopefully it is enough to motivate us in trying to understand this the early algebra better, and in particular in trying to address what is today's goal. So for me, today's goal is to understand what is the relation between this generalized Kac-Moody algebra obtained from as a Brochard's Lie algebra, given our BPS Lie algebra. So we want to understand the connection between this Lie algebra and another Lie algebra called the Maulik-Okounkov Lie algebra. And so I can already try to give you the answer because it's pretty exciting, at least from my perspective. And the answer is that up to some trivialities, these two Lie algebras are the same. But to understand the actual content of this statement, we first have to understand something about the Maulik-Okounkov Lie algebra. And this will be essentially the first cover the second section of my talk, the one that comes right after this reminder. So, what is the Maulik-Okounkov Lie algebra? So, this is a story that essentially started around 12 years ago, I think. And so it started with the study of quantum cohomology and also quantum K-theory of Nakajima quiver varieties. So this study led Maulik and Okounkov to define two representation theoretic objects. So first of all, we have the Maulik-Okounkov Lie algebra, which again looks like some kind of generalized Kac-Moody Lie algebra. So it has a triangular decomposition. But two things have to be stressed. So the first thing is that a priori, this is an algebra only defined over the base ring given by the T equivariant cohomology of the point. So, and here, so unlike in the theory of cohomological algebras, here we cannot choose T to be trivial. So in their definition, T cannot be chosen to be trivial. And so in particular, this will be an algebra defined a priori over some space of polynomials in some variables. And since the very beginning of this subject, people have been wondering whether it is possible to define this Maulik-Okounkov Lie algebra over the rational numbers and not over this space of polynomials. So actually, maybe here I should say polynomials over the rationals. And so today I will hopefully manage to explain why the answer is yes. And again, this comes from understanding the relation between the BPS Lie algebra and the Maulik-Okounkov Lie algebra. So this was the first important observation to make. So the base ring of the Lie algebra. And the second one is the fact that this is some kind of technicality, but still is important. So the Cartan part of the Maulik-Okounkov Lie algebra is twice as big as one might expect. So in principle, one from the theory of generalized Kac-Moody Lie algebra would expect that this is just essentially a bunch of copies of the rational, as many as the number of vertices in my quiver are. But actually, it is twice as big. So here we have two, we have the two, so we have twice as many copies. And so the reason it's quite stupid in the sense that this is not really a generalized Kac-Moody algebra. It has a very big center, and this center is exactly a copy of q to the q0. So this is central. Okay, this is a detail, but it is something to keep in mind if you want to understand today's statements. But yeah, having said that, let me also tell you that, as I said, this is one of the major outcomes of Maulik-Okounkov work. So defining the Maulik-Okounkov Lie algebra, but there's also another very interestingly theoretic object that carries their name. It is the so-called Maulik-Okounkov Yangian. So the Maulik-Okounkov Yangian is some non-commutative algebra acting, actually it's a bi-algebra, acting on the cohomology of quiver varieties. And interestingly, somehow in analogy with the theory of cohomological algebras, there is some sort of PBW type isomorphism in the sense that the associated gradient of the Maulik-Okounkov Yangian, taken with respect to some natural grading defined on the Yangian, is isomorphic to the universal enveloping algebra of the Maulik-Okounkov Lie algebra, and once again tensored with this cohomology, C-star equivalent cohomology of the point. So as you see, these kind of two PBW, the fact that geometry, let me say geometry related with studying modular spaces of quiver representations give rise to two Lie algebras, and this kind of PBW isomorphism that look like similar suggests us that there might be some relation between the Maulik-Okounkov Lie algebra and the BPS Lie algebra. So
the filtration is not of geometric origin.
The filtration it is in a sense of geometric origin, in the sense that somehow this Yangian will be obtained. So the Yangian, I will explain it later, will be obtained from R matrices, will be reconstructed from the R matrices essentially, so from the braidings of the category of representations. So these R matrices are constructed geometrically, and somehow the grading comes from there by taking so somehow this Yangian will be defined as the set of matrix coefficients of these R matrices, and these matrix coefficients carry a grading because the R matrix is an R matrix with a spectral parameter, and we can take the grading with respect to the spectral parameter.
But I'm a bit confused. When you write grading on the left-hand side, I assume that you have filtration only, not the grading, and you kind of continuously say grading.
Yes. I mean, we have a filtration on the left-hand side.
Yeah. Okay.
Yeah, I don't know if I said something else, but we have a filtration. And the filtration comes from the fact that essentially these are matrices, are spectral matrices, so it can be written as a formal power series in the spectral parameters. So okay, now let's start with the setting. So I guess this section is a bit tedious, but I guess it's also unavoidable. So let's try to be quick and effective on it. So let's start with a quiver. So for me, Q is the quiver with set of vertices Q0 and a set of edges Q1. So that for a quiver is something like this, for instance. So Q bar will be the double quiver, so we double all the arrows. And here you can appreciate the first typo. So this is alpha star. It was missing. And for me, QF would be a framed quiver. So for me, a framed quiver arises as soon as I choose a dimension vector f. So a string of the non-negative integers indexed on the vertices of the quiver. And so to frame a quiver, one adds some point at infinity, some vertex at infinity, and adds arrows from any vertex to the vertex at infinity as prescribed by these dimension vectors. So for instance, in this quiver, f will be a tuple of two non-negative integers, f1 and f2, and I add f1 many arrows from the first vertex to the vertex at infinity, and I do something analogous for the second vertex. And okay, whenever I have a space of representations for a double quiver, I have some kind of moment map landing in the Lie algebra of the group of automorphisms of this my space of representations. This is really a moment map in the sense of symplectic geometry, but for us today, this will not be so important. What will be important is that we can consider as soon as we are given this data, we can consider the stack quotient of the zero locus of the moment map modulo the automorphisms of my representations. So this is a stack quotient and gives rise to the modular stack of representations of the preprojective algebra of the quiver. And as Lucien discussed in his lectures, we have amorphism, some kind of Jordan-Holder filtration that for any closed point in my stack, so for an isoclass of representations, associate to it its semi-simplification. And as I write here, this lands in the Gaussian modular space, which is simply the spectrum of invariants of functions on my zero locus of the moment map. Okay, and the other ingredient I need to define is the Nakajima quiver variety. So for me, Nakajima quiver variety will go with the letter N. Oh, I'm sorry. We go with the letter N here. And so I think, I'm not sure this equality is really, I mean, it's natural, but maybe, I don't know if you have ever seen it. So my point is that it would be good for us to think of the Nakajima quiver variety as the good modular spaces parameterizing representations of the frame quiver with some prescribed stability condition. And so what I mean is that I will always think of my Nakajima variety. So usually, at least in my experience, Nakajima varieties are always thought as something coming by framing some quiver. So this might be the original quiver. So we frame it. So we add a copy of a vertex for any original vertex, and we add some maps connecting the original vertices to the new ones. So for me, it will be a bit more convenient to think of them in another way. So we can keep the original quiver as it was before, but now we only add a vertex at infinity with its dimension vector. The dimension vector of the vertex at infinity will always be 1. And we add some arrows from the original vertices. So from the vertices of the principal quiver to this vertex at infinity. So this is a classical construction, but I think that for us it would be important to think about the Nakajima varieties in this way, and think about that they are simply modular spaces of the preprojective algebras for this quiver with some stability condition. And for us, today we will always pick a very specific stability condition psi. This is stability condition saying that some module, so some in the space of representations of my frame quiver is stable if and only if there exists no submodule n supported only on the principal part of the quiver. So whose dimension at the vertex at infinity is 0. So that's what I state in this line.
So say again, so your stable representation is the one which, because
I
I'm
cannot have
confused.
submodules support.
But it's submodules for pre-projective algebra, yeah?
Yeah, on the principal part of the quiver, so not on the framing.
Yeah,
So,
does it mean that it's a trivial stability condition?
No, this is not a trivial stability condition. I think so. The point is that if I want the cohomological algebra to act on a quiver variety, and I want it to act, say, on the left, I have to pick up a specific stability condition, and this is the one. So this is a stability condition that ensures both that the cohomological algebra act on the quiver variety and that the quiver variety is smooth. So here, for this particular choice of stability condition, semi-stable is the same as stable.
Yeah, but you know, stability condition, of course, you can describe it in this way, but actually it is given by this collection of numbers like King stability condition.
Yeah. So I think
And
this is.
what are these numbers? So
I think it's either all ones or all minus ones, depending on your convention.
all ones or all minus ones in the for the original quiver for the quiver Q.
Exactly.
Okay.
So depending on you on your convention, this means, so if you pick this, so for my convention, for instance, if you take all ones, then you act your coacts on the left, and if you pick all minus one, your cohomological algebra acts on the right.
Okay.
But we have to choose one because unlike, so we'll see in principle for Maulik-Okounkov Yangians, we can pick any stability condition. But in the theory of cohomological algebras, if we want an action on quiver varieties, we have to be a bit careful. But okay, and so let's pass to torus actions. So for me, all the quivers today will be doubled. And so whenever the quiver is doubled, we also have an action of a two-dimensional torus T with two variables T1 and T2 spanning it. And they act in the way described by this diagram. So the variable T1 will rescale one arrow, and the variable T2 will rescale the other arrow. And just to connect with maybe other people's notation, what is usually called the Planck constant, so H bar, is just the product of T1 and T2.
So is it the same for all pairs of arrows, the same H
Yeah,
bar?
this is the same for all pair of arrows. So in principle, we can choose a larger torus. So what I actually want is that whatever torus I choose, there is a subtorus which acts like the T I describe in this slide. So all the arrows going of, let's say, of the undouble quiver are rescaled by T1, and all the arrows coming from doubling are rescaled by T2.
Let's see. So, does it mean that if I consider this double quiver, I mean representations of double quiver as a cotangent bundle to the representations of original quiver, so what will be the weight of the symplectic form?
Is exactly this H bar, T1, T2.
It will act as H, okay.
Yeah, exactly. And okay. And another important point is that whenever we add a framing, then we also get an action of the group that I denote in the following way. This is AF. So for me, AF is a torus of rank equal to the magnitude of the framing, so to the sum of all the entries of the framing vector. And so the action looks like the one I described with this picture. So you have your original vertex I of the quiver. So I is in Q0. So you have your vertex at infinity here. And so as prescribed by the framing procedure, you add all these arrows connecting the original quiver to the frame quiver. And so you can rescale each arrow by some parameter A, I, J in general. So that's the action I consider. So again, if you think of the quiver variety in this way, so this AF is simply some maximal torus in the product of GL Fi, where now the Fi live here. And let me also add the last subtlety, hopefully. So we can consider a one-dimensional subtorus. I denoted as C star infinity instead of AF. It is essentially the subtorus sending its, let's say, its spanning variable to a tuple O whose where all the variables are the same. So maybe I should write it without the brackets here. And essentially, the reason why I want to introduce this additional action is that whenever I consider some kind of moduli problems of representation, for instance, I want to consider the moduli stack of all representations. Usually, I have a sister action acting on the framing at infinity. So, and I want to kind of keep in mind that that sister action can be seen as a subtorus of this framing torus. And so as a consequence, I define AF0 as the quotient of AF by the C star 0. And by construction, the torus TF defined as the fiber product of T and AF, and also this TF0 defined analogously act on the cohomology of the quiver variety. Okay, so finally we have all the ingredients to discuss the Maulik-Okounkov Lie algebra. So, and to do that, I will rely on the following theorem, the following result of Maulik-Okounkov that says the following. So let's pick a co-character sigma of a subtorus A of my framing torus AF, and let's assume that this co-character is generic enough. And then Maulik and Okounkov tell us that then there exists a unique morphism of modulus over the equivalent cohomology, the TF equivalent cohomology of the point, that goes from the affix locus, the affix locus of my quiver variety to the cohomology of the whole quiver variety. And this is unique because we ask this morphism, which is called the stable envelope, for this choice of co-character sigma, to satisfy certain axioms. So I don't want to really dig into the axioms, it would take us too far away, but what I want to convey is more or less the philosophy behind the stable envelopes. So morally, the axioms defining the stable envelope say that the stable envelope for our choice of character sigma extend a class, so our cohomology class, defined on any component f of the affix locus of my quiver variety, to a class defined on the whole quiver variety. And we do it in a way that takes into account somehow the attracting set, so the attracting equivariant curves living in the quiver variety. So more formally, we require that this extension is supported on the so-called full attracting set of my chosen component f. meaning that this will be a union of attracting. This is a singular variety, very singular in general. And this is the union of all the attracting set for the components, connected components f prime, that are smaller than f with respect to a partial order that is defined with respect to the choice of co-character. So this is the formal definition. So f prime is smaller than f. I should say smaller or equal than f. Also here. If there exists a chain of connected components fixed by this A action, such that the closure of an attracting set of Fi intersected with Fi minus 1 is non-empty. So I think that, for instance, if you take the cotangent bundle of P1, so which is one of the easiest Nakajima varieties, so you think of it as a Riemann sphere, then you have two fixed components, which are just isolated points, 0 and infinity. And one attracting set is the 0 section of this cotangent bundle, and the other attracting set is the fiber at infinity. So for some choice of co-character. So for instance, the full attracting set of 0 will be the whole Riemann sphere plus this fiber at infinity. Okay, so actually,
is it
yeah,
a singular? Is it a Lagrangian subvariety?
yeah, it is Lagrangian but singular, correct? And it is Lagrangian because by assumption, sorry, but not by assumption, but by construction, my AF respects the symplectic form.
Okay.
Since it respects the symplectic form, this attracting set will be Lagrangian, smooth Lagrangian, and this union will not be smooth, but on the smooth locus it will be a Lagrangian submanifold. And so let me also say that actually the stable envelope for my choice of co-character sigma only depends on the component in the real Lie algebra of A where sigma live. And the component is defined with respect of some, oh, sorry, this is imprecise. So the real Lie algebra of A is co-character times R. So here, essentially, I'm cutting the real Lie algebra in pieces by means of some hyperplanes that have some geometric origin. I will not explain this, but the stable envelope will only depend on the component where this co-character lives inside of this wall and chamber arrangement. And this is a very important aspect. We'll dig into it soon. But before doing that, let me also add another piece of notation. Let's assume that we pick our framing F and we split in two pieces. So we assume that F is equal to F prime plus F double prime. And that, so for this given as a decomposition, we can fix a specific A, a specific torus A inside of the framing torus AF, such that the A fixed locus of my any quiver variety looks as follows. So it's a union of fiber product of smaller quiver varieties. And this is a very old result, but it's super important in Maulik-Okounkov theory and in general in understanding the representation theoretic content of the geometry of quiver varieties. So the reason why this result is important is that as soon as we define an F with this mat_BN as the direct sum of all cohomologies of quiver varieties for all dimension vectors D, so for all dimensions of the principal quiver, the original quiver, then by the Kunet formula, we can write the stable envelope like some kind of multiplication map. So you see, if I apply the Kunet formula here, and in addition, if I sum for all F prime and F double prime satisfying this condition, then I can rewrite the stable envelope in this way. And actually, the fact that this looks like some kind of multiplication map is important for us, will be important. Hopefully, I will be able to explain this and how this is related with cohomological algebras. But first things first, for this choice of A, so for the choice of A realizing the A fixed locus as a union of fiber products of quiver varieties, there are only two possible choices of co-character, sigma plus and sigma minus. I will denote them in this way. And then we define the R matrix as the transition matrix between stable envelopes for different choice of co-characters, sigma plus and sigma minus. And by construction, this will live in the endomorphism ring of this tensor product of two cohomologies of quiver varieties. And as you see, here I'm localizing in the sense that I'm inverting some equivalent parameters. And this is required to define the inverse of the stable envelope. So the stable envelope is an injective morphism of modulus over the cohomology of the point, but it is not invertible. And this is not invertible for degree reasons. For instance, it doesn't hit the zero-dimensional cohomology, the degree zero piece of the cohomology of the target. But if you localize enough, you get an isomorphism, and so you can invert.
Why there are only two choices? You have only two chambers.
Yeah, it is because of this very specific. So here I'm picking some very specific group A, such that the A fixed locus of my quiver variety will look like this. And for this A, one can dig a bit into the definitions and see that there are only two chambers. So somehow this torus will be a torus in two parameters, A1 and A2. And somehow the Lie algebra, so the real Lie algebra will be R2, and I will only have some hyperplane will be A1 equal A2. So this equation cuts the real algebra in two components. But things, you're right in the sense that things become very interesting as soon as there are many components in my Lie algebra. So more precisely, we have the following result by Maulik-Okounkov. So this operator R satisfies the Yang-Baxter equation in this endomorphism ring of a triple tensor product of cohomologies of quiver varieties. And so the argument here, I will not explain it in detail, but it's some kind of wall-crossing argument. So here the Lie algebra, since I'm adding more pieces in my tensor product, I will have exactly 3 hyperplanes, so I can jump between chambers in 2 different ways. And these 2 different ways reflect the 2 sides of my Yang-Baxter equation. And moreover, and this is the last, hopefully the last information about the R matrix I will provide you with, is that so the R matrix has an expansion like this. So it starts with 1, and then you can expand in certain equivariant parameters. These equivariant parameters are kind of perpendicular to the wall that is defining the R matrix. And as soon as I pick this equivalent parameter, this expansion is unique, and I have a classical R matrix, which is defined as the first coefficient of this expansion. Classical R matrix in the sense that it satisfies the classical Yang-Baxter equation, which is somehow the first degree approximation of the Yang-Baxter equation. And okay, finally, we have all the ingredients to define the Maulik-Okounkov Yangian. So I will not be too precise for time reasons, but let me say that the Maulik-Okounkov Yangian is some subalgebra of the algebra of endomorphisms of all quiver varieties, and it is generated by partial traces of all matrix coefficients of the classical R matrix and the higher coefficients of the R matrix. So instead, the Maulik-Okounkov Lie algebra, in the Maulik-Okounkov Lie algebra, one only allows R, so the classical R matrix. Once again, I'm sorry. So what I want to say now is that this is a Lie algebra over the T equivalent cohomology of the point. And once again, I want to stress that T in general will not be allowed to be the trivial torus. Again, it will be like the torus I introduced before with two parameters, T1 and T2. Well, in principle, one could only pick one, like H bar, but there must be at least H bar. And you can see it from here, essentially, because otherwise this whole construction dies, because if H bar is equal to 0, all the coefficients except 1 are 0.
I somehow missed the point, because I understand that it's an algebra. That's fine, associative algebra, but where did you get the Lie algebra?
So I'm not so in principle you can pick only you can only take partial traces of the classical R matrix, and then one can check this is something to prove that this is so in principle this Lie algebra, this space here, it's just I'm sorry, what's going on with my pencil? I don't know. My pencil has just died, but okay. So let's go on. The Maulik-Okounkov Lie algebra is a priori just a subspace of the Yangian, but one can check that this is closed under the bracket, and the bracket is the one induced by the algebra structure on the Yangian.
No, I do not understand, because I'm reading your definition, and you say that the Yangian of this Maulik-Okounkov is generated by partial traces. That's okay. But how you single out the Lie algebra itself from this algebra generated by traces? I missed somehow.
Because in the Yangian, you also allow higher coefficients of RK. So you allow all the coefficients. You consider.
Okay, but what is then this GMOT? It is generated by what? By matrix?
Partial traces of the classical R matrix.
Just by the classical R matrix.
Yeah, absolutely.
All right. Okay.
Okay. And so just to make things a bit more concrete, I will give you a set of spanning elements. So it is not trivial that the or what I say really spans the Maulik-Okounkov Lie algebra, but it's a result. It is correct. So in practice, the positive part of the Maulik-Okounkov Lie algebra is spanned by the following operators. So I call them psi alpha. These are in the again in the endomorphisms, in the product of all endomorphisms of the cohomologies of quiver varieties, and they are defined as follows. So their action on some beta, so living in some cohomology of quiver variety, is obtained by letting the R matrix act on the product of alpha and beta, and then by killing essentially one component of this tensor product by letting the vacuum vector act on the cohomology of the quiver variety. So in each cohomology of quiver variety, there's a vacuum vector, essentially the cohomology of the point variety. And okay, so we are finally get to the main result. So the first main result I want to advertise is the one obtained with Ben Davison, and it states that there is an algebra there is an isomorphism of ZQ0 graded, cohomological graded Lie algebras between the BPS Lie algebra, or well, more precisely, the generalized Kac-Moody Lie algebra arising from the positive part obtained as a BPS Lie algebra, and the Maulik-Okounkov Lie algebra. And these isomorphism intertwines their actions on the cohomology of the quiver varieties. And in particular, it follows that the Maulik-Okounkov Lie algebra is an extension of a Lie algebra defined over Q. So, as I said before, in the theory of Maulik-Okounkov, the torus T cannot be chosen to be trivial. However, you can do that in the theory of cohomological algebras, and you know that for different choices of T, the Lie algebras are simply related by base change. So, as an upshot of this theorem, we see that also the Maulik-Okounkov Lie algebra can be defined over the rational numbers, and simply we didn't know this because we couldn't compare it to the BPS Lie algebra. And this theorem has some cool corollaries. So the first corollary is that there is an isomorphism between the cohomological algebra and the positive part of the Youngian. Again, the Youngian also has some kind of triangular decomposition, and its positive part is isomorphic to the cohomological algebra of the preprojective algebra of the quiver. And once again, this isomorphism intertwines the action on the cohomology of the quiver varieties. So in particular, it follows that the action of the cohomological algebra on the cohomology of all quiver varieties is faithful, which was something expected, but I guess never proved before. Another cool thing is that from our result, it follows that Okounkov's conjecture is true. So what do you mean by this? It means that the graded dimensions of the positive part of the Maulik-Okounkov Lie algebra are given by the coefficients of the Katz polynomials. So the way this corollary follows from our theorem is that the result was known for the BPS Lie algebra. I think this was originally due to Maulik-Okounkov. And so since it was known for the BPS Lie algebra, and we know that the BPS Lie algebra is the same as the Maulik-Okounkov Lie algebra, then, well, the result follows.
Well, maybe Mozgovoi, did he work with BPS Lie algebras, or he works with Kochas? I don't remember.
So I guess he was working with critical cohomological algebra.
Yeah, but not with the Lie algebra. So first you have something for the associative algebra. Then, since you have this Davison Meinhardt, I mean, when you have
you're perfectly right. It's a combination of the Mozgov's result and the work of Ben and Meinhardt.
Yeah. Okay.
So in particular, you need dimensional reduction also to And okay, so since now all the results have been stated, I can hopefully give you an idea of how to prove them. But before doing that, let me try to restart my app because I don't know why my pen is not working anymore. Well, it is not working, but you see my mouse, right?
Yeah.
Okay,
Your
so I'm sorry. No, my pen has died, but I can use my mouse to comment on things. Luckily, I have the notes. So how to prove the main result? So the idea is to use something called non-abelian stable ambiguity. And so to begin with, let me state another result. Again, obtained together with Davison. And this is kind of the main tool to prove theorem 1, but I guess it's also something interesting by itself. So let's assume that our framing vector f is different from 0. Then the theorem says that there exists an injective morphism, I call it psi fd, from the cohomology of my chosen quiver variety to the cohomological algebra for the framed quiver. So here I'm considering the cohomological algebra of the preprojective algebra of the framed quiver. And this is kind of natural because I want to connect with quiver varieties which are framed. And what we do with Ben is that we construct an injective morphism between these two spaces. And not only we do that, we notice that. So remember that before in the second section, so the one about the conventions, I distinguished before the torus TF and TF0. So TF0 was just a quotient of TF by some trivial one-dimensional subtorus. So a subtorus that was acting trivial on the quiver variety, but that was involved in the definition, essentially in the definition of the cohomological algebra, because the cohomological algebra is defined starting from the stack quotient of representations. So here we are considering frame representations. So we have these automorphisms of the vertex at infinity that gives this C-star action. But anyway, so we can see that TF0 cohomology of the quiver variety as a subspace of the TF cohomology, TF equivalent cohomology. But if we restrict our map psi to this subspace, then we can see that this psi map sends this piece of the cohomology of the quiver variety to what? Exactly to the BPS Lie algebra for the projective algebra of the frame quiver with this specific dimension vector D1.
How do you see that?
How do we see this?
Uh-huh.
So this is non-trivial. So first of all, this psi map, so I also say it in a remark below. This psi map is something that we borrow from Maulik and Okounkov. So in the sense they call it non-abelian stable envelope. I think it should be called non-abelian stable envelope. And they use it in a totally different setting. They use it in the context of enumerative counts of quasi-map from some curve C to Nakajima quiver varieties. So that's not the way we do that. We see that. We see this map, but like them, we interpret them as a correspondence. So we interpret as a correspondence, but we also show that it comes from amorphisms between the relevant sheaves in the bounded derived category of sheaves on some good moduli space. So we have a sheaf theoretic interpretation of this map, and we see that this map preserves the relevant perverse filtrations on the domain and the target. And we show that if we pick the degree 0 piece of this filtration, which is the first piece because they start from the degree 0 piece. On the domain, we get exactly this space, and on the target, the BPS Lie algebra.
Is the curve CP1?
So I think that a priori, Nakajima allow C.
Yeah, but in your story.
But in practice for applications, so they pick C equal to P1.
Okay.
Yeah. So that's the origin of their map. So we try to give it another life, and so that's our what we do. And so I guess 1 hour have passed. I have a few things to say, but
Yeah, you
But
can say
let's
it
see,
in
do we
this.
have like 10 more minutes?
Yeah, you have it. Yeah.
Okay, thanks. So first of all, let me say that one reason why this map is called non-abelian stable envelope is like, so for the stable envelope we hopefully and we have seen that the stable envelope is some kind of map solving an extension problem. And the extension problem in the case of the original stable envelope, the one I discussed before, is that it picks a class on some a fixed component, so some components with respect to some torus action, and it extends it on the whole space where this component lives, but it does in some kind of controlled way. So it does it along somehow following the geometry of the attracting set in my variety. So this non-abelian stable envelope should be thought as a map extending a class from the semi-stable locus. So the quiver variety involves picking a quiver variety involves a choice of stability condition. But we can think of this quiver variety living in some ambient stack, okay? And we want to extend this class from this semi-stable locus to the whole stack. And I guess that's the way one should think about this psi map, this non-abelian stable envelope. And maybe let me tell you a few more things. So much of our work is consisting proving theorem 2 and showing that it implies theorem 1. So let's try to see a bit how theorem 2 implies theorem 1. So as a first step, we notice that if we pick some framing vector whose entries are all different from 0, then by exploiting Maulik-Okounkov work, we see that the Maulik-Okounkov Lie algebra embeds in this endomorphism of cohomologies of quiver varieties. So similarly, we show that the action of the preprojective algebra of the unframed quiver on the preprojective on the BPS Lie algebra of the framed quiver. So you can always think of the unframed quiver as living inside the framed quiver, right? So you can the BPS Lie algebra of the unframed quiver acts on the framed one simply by brackets. And so we show that also this BPS Lie algebra embeds in the endomorphisms, in the endomorphism ring of these of these here I guess there's a typo. Luckily my pen is working again. So here I should write embeds in the product for I in Q0 of the endomorphism of TF delta I. So as a second step of our proof, we show that this psi map, this non-abelian stable envelope, adjoins between these product of endomorphism rings, where both the Maulik-Okounkov Lie algebra, or at least its positive part, and the BPS Lie algebra live. So what remains to prove for us is to show that this isomorphism induces an isomorphism here, right? And which is exactly the concept of the step 3 that I state here. And in practice, and this is where I really wanted to get, is that this statement, so the fact that is a adjunction by the psi map, the non-abelian stable envelope, induces an isomorphism between this Lie algebra, boils down to the following statement, which is something that I would really like to comment here. So once again, remember, I'm sorry that there's a lot of notation to remember. So first of all, and also not only a lot of notation, but probably also a bit of bad notation. So this psi of A was the generator of the BPS, of the Maulik-Okounkov Lie algebra. So it was the one, so psi of alpha of beta was defined by taking some partial trace of the classical R matrix eating alpha times beta. So it was this object here. So this is the vacuum vector. And maybe just to match notation here, I should write some f prime. Okay, so the idea is that I consider this operator, I let it act psi alpha, I let it act on beta, and then I feed it to my psi map, to my non-abelian stable envelope. The reason why I said bad notation before is that this psi here has nothing to do with non-abelian stable envelopes. So maybe I should have called it phi. So let's say phi. Okay. And then what we show is that this is essentially the same as taking the Lie bracket of the images of alpha and beta by the non-abelian stable envelope. So notice that taking the bracket involves taking the Koch multiplication. And then taking the coproduct. So also the cohomological algebra is a B algebra, so it has a coproduct. And so first we take the product and then the coproduct.
Hold on. Does it
Yeah.
have a coproduct? Or I forgot. Or it's just for the pre-projective health? In general, it does not.
So I think in general it might not have it. I'm not sure. Surely it does have it in the case of the pre-projective algebra.
Okay.
So somehow the reason why I think that this statement is interesting is that, so if you think about the classical R matrix, somehow the classical R matrix comes from composing stable envelope for different, or more precisely, composing a stable envelope with the inverse of a stable envelope for another chamber. Okay? And instead here, what we are doing is that first we are taking the product of these classes psi alpha and psi beta, and then we are taking the coproduct. And you see that there's some kind of similarity. So stable envelope, because the coproduct is somehow recovered from the product in the cohomological algebra by somehow reading all correspondences backwards. And this is actually also what happens in the theory of stable envelopes. So if you pass from a chamber to the opposite chamber, somehow you recover the inverse of the stable envelope by reading the correspondence defining the stable envelope backwards. So this is kind of the technical reason why this statement holds. Of course, it is a bit tricky to prove. It's not this simple, but that's essentially the philosophical reason why such a statement should hold, because somehow stable envelope and its inverse for different chambers should be thought of like product and coproduct in the cohomological algebra. So in principle, I will have a bit more details, but I think it's we can safely skip them and just try to formalize a bit more precisely what I said before about similarities between a stable envelope and products in cohomological algebra. And so I will do it by means of the following proposition, which, so I first proved and then we reproved by different means with Ben. And it says the following thing. So, okay, so there's a very hard way of reading this statement, and it's just by looking at all the details of this diagram, or trying to forget almost all details and getting the idea. So I will try to explain you in the second way. So think of this side of the diagram. It's just the stable envelope. Okay, so you start with two quiver varieties. You think of them as the tensor product of the cohomologies as the cohomology of the fiber product. Okay, so this is a variety. You can think of this as a fixed component in some larger quiver variety. This is the target of my stable envelope. Okay, so the stable envelope will give me a map between these spaces. On the other hand, you can consider the cohomological algebra for the preprojective algebra of the quiver. So here, technically, the quiver should be the following quiver. So you have your original quiver, and since here you have two copies of the quiver varieties, you have to add two pairs of vertices at infinity, with some maps connecting them, depending on f prime and f double prime. Okay, but okay, so on the right hand side there is some cohomological algebra, and the statement of this proposition says that the diagram where I well, let me state it in the following way. So these psi maps of the non-abelian stable envelope identifies the cohomological algebra multiplication, the cohomultiplication, with the stable envelope. So you see that both here and here have the non-abelian stable envelope. So in other words, another way of saying this is that the multiplication of this specific type of cohomological algebra restricts on the semi-stable locus to the stable envelope, and the restriction is obtained by means of this non-abelian stable envelope. So I guess that this is the reason why it is possible to prove this technical result up here, and also why it's actually the deeper reason why Maulik-Okounkov Lie algebras and BPS Lie algebras are the same. So this is also a good point to end the talk, at least, or more precisely to give you the chance to ask some questions if you have any.
Yeah, thank you very much. Yeah, so this mysterious non-commutative stable envelope, it's kind of the key for the interaction between Maulik-Okounkov. So then it's, I really, I must confess, I really didn't understand why it works. By the way, for Koha of preprojective algebra, you can go up to dimension 3. Yeah, instead of doing dimensional reduction, you can consider the corresponding sort of a local 3 Calabi-Yau category. But as for the Maulik and Okounkov part, can you upgrade kind of your diagram to the statement about 3 Calabi-Yau, about quivers with potential?
I'm not sure. This is indeed an interesting question. So it would be about defining a stable envelope for a space with a potential. And this is something that I think it has never been done before. I think there are some. I think it would be the right moment now to address this question, but I'm not sure how. I don't think this has ever been done.
You see, I mean, I haven't thought about that, but you know, on this stable envelope side, you have this Lagrangian skeleton, this stable envelope. Yeah, and well, of course, nothing is derived here. It's in a sense more or less abelian categories. But I know that Adil Khan with Kinja, they try to interpret three-dimensional Koha, at least for local Calabi-Yaus, using certain derived Lagrangian correspondence as a correspondence as a kernel, as a correspondence which defines you the product in Koha. So I'm just curious.
I think that's a reasonable approach. But I'm not confident enough to say something about it. Like, it's not something that I've been trying to do really.
Yeah, and another thing maybe kind of more elementary. So for the Yangian, you have the full quantum group. You mean that it's not just one half, but the whole thing. Now, for Koha, you have in general one half, but for pre-projective algebra, you said that you have a coproduct, but in order to get the other half, you need, I believe, sort of a scalar product compatible. Okay.
Yeah.
So is it possible to, because I forgot what Lucien told us, is it possible to construct the full Koha for the pre-projective algebra intrinsically?
So intrinsically via geometry, I don't think so. Like, I don't see a way of doing that.
Yeah,
of course, you
then
can try to do some algebraic Dreamfield double, but that's not the question.
Yeah, but that's, yeah, all right. Because for Maulik and Okounkov, you do have this kind of geometric description of the whole thing, not just positive.
Exactly, because you have the whole R matrix, not only.
Yeah, and here it's somehow you do have a relation between positive parts using this non-commutative stable, but you do not have a relation between full.
I mean, as soon as we have the relation,
yeah, you can prove it, but it's not
right. Yeah, you have we can prove it, but it's not like it doesn't come naturally from the geometric object.
Yeah, that's what I mean. Okay, and maybe the last question. I assume that if you change the cohomology theory, you get quantum affine algebra. You get quantum group. I mean,
that's correct.
Yeah. Okay. All right. So more questions?
Yes. Could you explain what this Maulik-Okounkov conjecture on this X polynomial, which is that's the main statement in the paper?
Yeah. So yeah, we can have a look at it again. So maybe I will start just by rephrasing it. So the Maulik-Okounkov Lie algebra has two gradings. So one is the cohomological grading, and the other one is the grading by the dimension vector of my quiver representation. So one is D, and the other one is K. So K is the cohomological grading, and D is the dimension vector. Okay, so and this Okounkov conjecture, that I think it was formulated around 10 years ago, just right after the Maulik-Okounkov Lie algebra appeared, is that the graded dimensions of the Maulik-Okounkov Lie algebra graded with respect to the cohomological grading give the coefficients of the Katz polynomials. So here on the right I have the Katz polynomial simply. So somehow this also explains that tells us that this Maulik-Okounkov is highly non-trivial in even in high cohomological degrees for arbitrary quivers. And so it is not just maybe, I don't know. So even for many Dinkin quivers, it is not concentrated in degrees here. It's really something bigger. But once again, the way we get this result is that we inherit it from the analogous result at the level of cohomological algebras. So if you look at it from purely from Maulik-Okounkov theory, it is not. I don't know. I mean, there's no proof. There's no direct proof.
Mm-hmm.
So
is that for each fixed D, that is a Lie algebra, greater than Lie algebra by K.
Oh, sorry. So maybe there's a typo. So here, there's no
Because
T.
it depends on the dimension vector D.
Depends on D, yeah. So D defines the representation. So for every D, I have a Katz polynomial. Like counting absolute indecomposable representations of some dimension D. And
that's right. That's
so
what
in my
side.
so in my Maulik-Okounkov Lie algebra, in a positive part, I can this is the direct sum of the Maulik-Okounkov Lie algebra for all dimension vectors D. Okay, and this is the sum over D. And each of these pieces also has a cohomological degree. And this is the one that I pick by fixing some K.
And then you take the Euler characteristic of
Yeah.
well, I see that's yeah, you're taking the greater dimension, so you're writing
Correct.
right.
Yes.
Okay.
Yeah, by the way,
And
I remember
the D algebra structure is actually double graded D algebra, right? It's both D graded or it's
the Lie algebra is
each
degraded.
D is just it's a homogeneous component of the D algebra.
that's
Am I
correct.
right?
It's like the Katz
yes.
conjecture. Yeah.
Okay, good.
Actually, yeah. I think at the level of cohomological whole algebra, we somehow formulated it with Maxime long ago. But I have a question. I have some, again, it's sort of long ago. There is an analog of the Katz polynomial for counting of absolutely indecomposable vector bundles on the curve of a finite field. I think it was introduced by Schiffman. And I remember, I forgot because it's more or less the same time, like 2012. I had an idea that you can look for cohomological whole algebra corresponding to the quiver, not to the quiver, sorry, to the character variety of this curve. So it's two-dimensional Calabi-Yau, but I thought in terms of three-dimensional Calabi-Yaus, like you can upgrade it. And so kind of my question is either a geometric analog of this corollary 2, which is written here. And on the right-hand side, you would have this Schiffman analog of the Katz polynomial. And on the left-hand side, you have something which I don't know what. Maybe something coming with from...
So I think that the story is that there... So I'm not sure I remember.
Maybe Ben, I remember Ben told me he did something about character variety and cohas, but I don't remember him telling me that.
Yeah, so I think I'm not sure. There might be something related to the non-abelian Hodge isomorphism, right? Relating character varieties with
Yeah, maybe provided that you know.
Yeah, and then you have some coha to consider using that.
Okay, yeah, I would be interested kind of if you or Ben or whoever give me kind of reference. Okay, all right. Yeah. Any more questions?
Oh yes. So far here, the quiver is just an arbitrary finite quiver. What have you considered the possibility that quiver with automorphisms? So, for example, corresponding to non-simple lists, Katsumudi algebra.
Yeah. This is an arbitrary finite quiver. So we assume that the number of vertices is finite, and that's it. and also values.
Well, actually, in the corresponding cohomological algebra here, which always corresponds to the symmetric type of the algebra. So, for example, the root system of type B and C.
See, yeah.
Can you also, I mean, in those cases, the polynomials are constants. So what are they, or even the affine cohomological algebra of type B and C. So in those cases, polynomials are just polynomial for just, if not constant, will be degree 1. Oh, I probably don't want to say that. So in this case, how the Lie algebra is
So I'm not sure I got the question. Sorry, can you say it again?
well, so for example, I want to get a feeling how the root system for the corresponding to the Lie algebra type B and C.
Yeah,
Simple Lie algebra type B and C, which you don't have a quiver. You only have depends on how you, for example, for G2, you get A3, or they actually D4, but folding 3 vertices outside to form the G2 quiver, to form the G2 root system. But the corresponding quiver is not a G2 quiver, it's a D4 quiver.
Yeah.
So the D4, but gives the Lie algebra, which is the D4 Lie algebra. But if you look at the equivalent, by taking the quotient, that gets the G2 root system. So that's in those cases, the quiver corresponding to the valued quiver representations. There are also polynomials for those valued quivers.
Yeah, I'm not sure how to.
Okay.
I'm not sure.
And not much is known. Only in the finite cases that on the right-hand side, the polynomials were computed. Because in the finite case, you know what the polynomials look like.
Yeah, I'm not sure. I have to think about it.
Okay, well, thank you. That's very interesting. That was a curious question for over 20 years, at least, well, more than 20 years, 30, 40 years.
Okay, any more questions? Well, if not, let's thank Tommaso for a very interesting talk. And I assume that not everything is in the archive. Your paper is in the archive, but your paper with Ben.
Yeah, it is on the archive. The one with
it is. All right.
Yeah. We are about to upload a new version with some improvement, but it is already.
Okay, great. Okay, well, thank you very much. And
Okay.
this is it for today.